did a great job, and that will make my own work easy. So just as we discussed yesterday in the lecture, that if you are looking at a particular protein that is not yet in the PDB, that's protein data bank, and you actually need to do some analysis with that protein, then how do you go about it? So to go about it is called homology modeling or protein tertiary structure prediction. So I will be using the same uniprots that we used in the previous lecture. So I'll just share my screen and then try to get everybody along as I go display. Okay, so because of time, I already opened those tabs on my browser. So I'll just start all over again so that we can see. So directly, you could just type uniprots. I know you've done some jobs on uniprots prior now. So you could just type uniprots on your browser and then it's going to bring out this interface. Sorry, are we all following? Hello.
Yes, we are. Yes, we are.
All right, thank you so much. So I think probably what I should do first is to open PDB. So let's type PDB on the...
So your line is breaking, Dr. Anna.
Oh.
Is
How
it
about
your
now?
network? Okay?
Is it good now?
It's not. It's okay. I think it's the network over there.
Oh, no. But can we see my screen?
Yes, we can.
Okay. So if you look at the page I opened, you see RCSB PDB home page. So if you have the same thing right now, you can just click on that first link. It's going to direct you to this part. So you'll see this entry box, enter search items. So you see this entry box. If it's a protein that is, okay, maybe I'll just copy and then, okay, sorry. Let me just copy the website and paste it on the chat. Okay, thank you very much. I think someone already pasted it on the chat. Thank you very much for that. So are we all on the same page?
Yes.
Okay. So if you see this, where you have 3D structures, so that question mark, if you need more information on it, you can actually click on it. It will give you more information, but you see this enter search items, entry ID or sequence. So what they do on PDBs, they've given those different proteins PDB code or PDB ID. So if it's a protein that you know your code already, you can easily type your code. So I'm going to use an example of a code 3DHE. So you see it's going to come up because I already know that code. So the protein I'll be using is 17 beta HSD type 3, and that's a testicular protein. So let's go from, probably I don't know the code before, and I need that protein from the protein data bank. I'll just type in my protein 17 beta. You'll see that several results will keep coming out. Dash HSD, well, let me just use what it has. Hydroxysteroid dehydrogenase. So through literature, I already know that my own protein I'm looking for is type 3. So depending on what your target is, what you want to work on, will depend on what you're going to search on PDB. So let me put type 3. So it looks like the protein isn't here because it did not come up on the search engine. So now it's not just going to give me anything blank, but it will bring out proteins that are similar. So this is 17 beta HSD. It's also Homo sapien. So if you click on it, it's going to give you more information. There's a publication that you can actually read to have more information on it. So this is how to use PDB. So this is going to tell you the gene, then the PDB primary data. It's Homo sapien, that means it's human. Then can we see this code? Find protein for P14061. This is the UniProt code. So you can either write out this code and then go and search for it on UniProt, as Dr. Fatoke has been taking us through before now. So it has several. With this UniProt code, it's going to help you to actually know which organ this protein is from, because this same 17 beta HSD is in the mammary gland. But what I want to actually work on is the 17 beta HSD from the testis or the testicular organ. So with this code I have now, so because I've done this before, it's giving me, I already have the idea that, so we can see this literature that has already given us more information that this is type 1 and it's from the mammary gland. So if you read this PubMed abstract, as I said before, that there's a publication on it already that you can read. It will give you more information. And from this PubMed abstract, you can see that it's from the mammary gland. So this is not what I need. So to cut the long story short, from all I can say from PDB, my protein is actually not on PDB. That means it has not been crystallized yet. And what I want is 17 beta HSD in testes. So I'm going to do homology modeling. Since we already have, just as Dr. Fatoke has been taking us through before, pairwise sequence alignments, multiple sequence alignments, to help us to know which protein is actually similar to our own protein. And through that one that is similar, we can then probably predict the tertiary structure of what we actually want to work on. So I'll go to UniProt and copy the link and send it to the group. So that's the link for UniProt. So just as I said in yesterday's lecture, that you can find majorly all proteins on UniProt. So you can also still search from this box, find your protein. Then you can search, I'll just put 17 beta HSD and then search. So now UniProt is going to bring out several proteins, similar protein of different organisms. So if you want to streamline your results, you can just click on human. So this takes you directly to human because I'm interested in human. So if you look at where my cursor is, you'll see the third entry. That is 17 beta HSD type 3, which looks like what I actually want. So you click on the code and then it's going to bring you to this page where it's going to give you other informations about that protein. So if you read it through, because the protein works with a cofactor, which is NAP-P, and they've also crystallized it with, they've also done some computational studies with the chemical it works with in the system, and so that's why you can see all of this. So this is going to help us by the time you want to do your docking with probably your own ligand, your special ligand, you dock it together with the cofactors and the other chemical that it works with. So you're not just docking with one single, with just the protein, but with the cofactors that the protein also has. So you can keep going. You have several informations about it. So these are several informations, but I just want us to get to the point where we'll get to the faster sequence and then copy that. So it's that faster sequence we are going to use for our homology model. So you can just take your time to do all of these studies, read, and then it will help you to have information about your protein. So if you can see my screen, at this page, I already have the faster sequence. So I'm going to click on download. So once you download, it's going to bring you to this page where you have the amino acid sequence. So you just copy, just as you did in previous lecture. You could either copy it and place it on MS Word or a text editor. So since what I need is just this faster sequence, I don't know if I'm too fast. Are we all on the same page?
I am too fast.
I'm too fast, I'm sorry. Okay,
Yeah,
so should I go back?
Ma, please start from the protein you are using so that we could follow what you are doing and replicate on our system so we can be able to ask you questions when need be. Thank you very much.
Okay, so let's just go from the beginning. I'm sorry, I'm pressed for time, that's why. So are we all on this page? If you just click on the UniProt link, it's going to bring you. Are we all on this page?
Yes, ma.
Yes, ma'am.
Okay. So as I said before that the protein is 17 beta HSD. Maybe I should copy this also and put in. Okay, so I just typed the page. I just sent it to the chat box. So if you just copy that protein on this find your protein box and then click search. Are we here?
Yes, ma'am.
Okay, thank you, ma'am. So I said to streamline our search because it's going to bring out searches for different organisms. You see mouse, human, rats, bovine, zebrafish, lots of organisms that has this same protein. But I'm interested in human. So I'll go to the human. Can you see where my cursor is? Then I click on human. Can I continue?
That's fine.
Okay, so it has streamlined my search to just humans. So I said I'm interested because through literature, I've already read the type of protein I need, and it is type 3 of the 17 beta hydroxysteroid dehydrogenase type 3. So that's the one I'm interested in, which is not in the PDB. And if you look at the entry, it's on number 3. So you just click on the number 3, the PDB code. The UniProt code. So you click on number 3. And over here, we have all of the informations with regards to the protein. So you can also do blasts here. If you blast it just as you've done in the previous lecture with Dr. Fatoki, it's going to give you a protein that's crystallized already in the PDB that is very similar to what you have. So we can also do that, as that will give us a template for our work. But there's an opportunity in Swiss model to build or to predict protein tertiary structure without a template. So we could try the two. So just click on blast. So you've done that before, that should be easier. So once you click on blast, it's going to bring you to this page. Are we here?
No, ma'am.
Okay, let me go back. So is this place cool? Are we all here?
Yes, ma'am.
Okay, so this was where we started from, that I streamlined it to human. Then I already said the protein of interest for me that looks like what I want is the third one. That's the type 3, 17 beta HSD, type 3. And it's Homo sapien, it's human. So I'm interested in this one, which is number 3. So we can click on the number 3, that's the UniProt code. So it will bring you to this page. So are we on this page?
Yes, ma'am.
Okay. So we'll see blast, you see blast, you see align, download, add a publication, entry feedback, and all of that. Can we see that line where we have blast?
Yes, ma'am.
Okay, so let's click on blast.
Yes.
Okay, so let's click on blast. So the essence of blast, as what Dr. Fatoki have said before, is going to help us to bring out other proteins that has been crystallized and is on the PDB that you can use as templates for your own protein that has not been crystallized. You can use it as templates to predict your own protein tertiary structure. So as we have understanding about protein, that protein is like buildup of amino acids. So we can see all these M, G, D, V, there are several amino acids. And if we just have this sequence, we only have the primary structure of the protein, but we cannot predict how the protein will fold into its tertiary structure. So that's what we want to do now, to know, since we have the primary sequence of the protein, then we want to predict the tertiary structure, how it's going to fold. So we want to predict protein folding. So that's what we want to predict. And there are databases where you can do that, just as we learned yesterday. So if you're all on this page, I'll go ahead and blast. So you can see in the advanced parameters, you have the opportunity to pick what you actually want. So if you see the sequence type, since we are working on protein, we are going to leave it at protein. Then the program, blast P, because we are working on protein. Blast X is for DNA or RNA. So since we are working with protein, we'll leave it at P. Then your threshold, you can leave it at 10 so that you have like a wider view of similar proteins. And then it has to be on this blossom 62. This is automatic. And you can leave every other thing at that, then run blast. So blast is running, we'll just give it time. And for this one, you don't need to input your email. It's going to give you the results from here. Are we all on the same page? Yes. No, fine. I don't know if it's my network. I don't know why it's taking time.
Last is still running.
Yes, it's still running yet.
Our own is still running too.
Okay. Just wait.
Blast, please.
Okay, so another thing we can do while that is running, we can actually copy our sequence and then use the Swiss model to build the protein tertiary structure without this. The essence of this is for us to have a template, because once blast is completed, we're going to see the protein that is highly similar to us, and then we can use that as templates in the homology building. But because of time, I just want us to, we could leave the blast still running and then just open UniProt on the browser and do the same sort of things that we did before. 17 data, interesting. Go to human, then the number 3. So are we here? Let's just open another page and then get the faster sequence. Okay. So we can leave the blast running underneath, and then let's reopen the UniProt and do same sort of things we did at the beginning, so that we'll get our sequence. Is that possible? Okay. Let's check. Oh, mine is still running. I think Dr. Zainab's one has completed, but mine is still okay. A few people. Okay, yes, mine is also completed.
Completed.
Okay, good. So let's click on the completed, then it's going to bring out the results.
Yeah, I could say
No,
completed.
this is now 7 beside was the theory. That's what we did before. No,
Oh,
mine
oh.
is we did before.
Nǹkan mi ló get in Bonnie.
Are we here?
It
Are
has
we on
brought
this?
the
It has brought out several results.
nǹkan mi lèmi wá rí báyìí o.
Wow. It brought out
It brought
250
the
results found. When you click on the
my own
completed.
it brought the original.
It's 250. It looks like original because
It's not 250.
Yes, the first
This one
one is
just
the
gave me another
original. The first, so
thing
if your
said,
blast is
3D
completed,
ló wà.
okay, let me go back. So can you see this interface, this space where it showed completed? Can you see this place where
I'm following. Yes, yes.
okay, so just click on the completed, then it's going to bring out all the results. It says blast 250 results found in UniProt KB. Are we all on this page? So if you keep looking at it, the first one is our actual protein, the one that we blasted before now, that showed Homo sapien. Then, so that showed 100%. The next one is from another organism that showed 98.4%. So it keeps reducing. This is from chimpanzee, also 98%, gorilla, 98%. So several other organisms also that looks like it. So I'm still going to click on the first one, since that's what I'm interested in, not on these other ones. If we click on the other ones, we are going to see the PDB code, and we can actually, so if I want to, so the next one that is close to it is that of chimpanzee, which is 98.7%. I can click on this, then it's going to give me the PDB code if it's been crystallized. So if we look at this also, it showed us that it's computationally mapped potential isoform sequence. So this is not also on the PDB. So, and I'm not interested in whatsoever is not on the PDB because it's still the same thing with what I have before. So I'll just go back. Okay, sir.
Hello, madam.
Yes, sir.
Okay, I think if you click on structure, we have okay, this particular place. Okay,
Yes,
so we can see from here that something is not available.
exactly. So if you
So-
even look at the down part, you're going to see they already said it's computationally mapped. If it were to be available, they're going to give us the PDB code. So let's go back to the first one, which is the one we are interested at. So just click the first one. Click the first one that has entry code P37058. Let me put the code on. 37058. So that's the one we are interested in. So let's just click this first one. So are we here? So if you look at the structure and on the 3D structure database, is giving us some vital information that this protein is actually on alpha fold. And then with this R code, we can search for it on alpha fold and just use the structure directly. Alpha fold is also another good, so I could just let me put the link for alpha fold on the chat so that we can also use it. It's actually a good one to also use whenever your protein is not on the PDB. It's highly recognized and it's publishable. So we can always use AlphaFold also if the protein is not on the PDB. And they've already given us the information that it's already on AlphaFold, so we are good to go. But for the purpose of the lecture, I just want us to continue with the homology build-up. So if we're on this page, let's click on download. We want to get the faster sequence. Are we all on this page? Well, someone said the structure is not showing. It could be network. But just don't worry about the structure. Go back to download. We are not interested in the structure now. Okay, so someone has even given direction on how to go about it. But just click on download. We are not really interested in the structure right now. So can you see this place where you have tools, download? We can click on download. Okay. So I'm at the top now where you have the code and it's also telling us that it's human. So can you see the way I'm scrolling down? So just keep scrolling down. you'll see different sections, name and taxonomy, subcellular location, disease and variants, features, keywords, PTM processing, interaction, then structure, 3D structure database, family and domains. So if we have the time, you should actually take your time to go through all of this because they are important informations. And it also told us that it's from testosterone 17 beta HSD3, which is my protein of interest. So where you see the download is the sequence and isoforms. Okay, exactly. So it's sequence and isoform. Then you click on download. Once you click on download, it's going to bring you to the page where you have the amino acid sequence. Then you copy that from the beginning, from the greater than sign, SP, and likes. So you click on, you copy that. You can either paste it on MS Word or text editor. So I copied it to my text editor. Then you go to Swiss model. So that's the link for Swiss model. So are we all on Swiss model now?
Not yet, ma, no.
Okay, I'll wait. So are we there now?
Yes.
Okay. So if we're on Swiss model, by the right, you're going to see supported inputs. The first one, you have sequences. So if you click on that sequences, you have some other options to click. Is it a single target example or multiple target example? But for the purpose of this presentation, I'll just leave it at that. I won't click any one. So just as I was saying before, if you have a template.
Excuse me.
Okay.
Please, my interface is not like yours. What I have on my screen is Swiss model, then repository beside it.
Okay, let me go back from the beginning and see. So, oh, okay. Yeah. Sorry about that. I already opened it down. So, you're on this interface, I think, right?
Yes.
Click on Start Modeling. Start Modeling. Are we out there? So this is what the first page will look like. Repository, then you see the Start Modeling button. Just click on this Start Modeling. So are we all on this page?
Yes.
Okay. So just as I was saying before, by the right, you are going to see supported inputs. The first one is sequence or sequences. That's if you don't have a template, then you can click on that sequence. But if you have a template, you can click on the target template alignment or users templates. So you can either click on target template alignment or users templates. So if you click on the users template, it's going to give you an opportunity to be able to upload your own particular templates. So what that means is that it's going to thread the primary sequences, that's the amino acid sequence, almost similar to the way your template is. But so as I said before, that for the purpose of this presentation, we'll just use the sequence, which is the first one. So can we see this box where we have paste your target sequence or sequences?
Yes.
Okay, so we can go back to our sequence that we saved on, that we pasted on MS Word or text editor. So just copy that, just as you did before, copy it from the greater than sign. And then paste it on this box. So do we have this?
Yes.
Okay, so if you want to title the job, you can, it's actually optional. You can title it so that by the time it brings out the results, HSD. So you could put that title 17-bit HSD. So if you want the results to be sent to your email, that's optional. So you can put it there or leave it. So are we all on this page?
Yes.
Okay, so we can click on build model. Build model. So it's running now. So are we here?
Yes.
Okay. So it's going to take time to build the model. So while that is running at the background, I could just quickly show us AlphaFold. So that's the link to AlphaFold. So because we already got the information that our protein is on AlphaFold, we can just type in the UniProt code. Directly to AlphaFold. Is going to take us there directly. But if we actually didn't take our time to read those information and we are not sure if our protein is on AlphaFold, we can do the same search as we did on UniProt. Okay, Swiss is still running, so we can continue with the AlphaFold. So once I click on that protein, this is the structure. So I can download this structure directly and I can do whatsoever I want to do. I could do molecular docking or simulations with this structure directly. But it's always good to have like 1 to 3, because by the time you get to your docking, this structure may not really give, you could have like some steric hindrances and the like. So that's why it's always good to have about 2 structures. So I can download this directly from AlphaFold and continue to dock with whatsoever tool you want to use. It could be Autodock, Vina, or Schrodinger Maestro to dock, and then continue with my further computational analysis. So let's go back to Swiss. Swiss is still running. So if your protein of interest is on AlphaFold, then you are good to go. You can use the structure from AlphaFold directly. But like what I said, it's always good to have at least your homology build-up modeling, that's the protein tertiary structure prediction, and then that of AlphaFold, because by the time you put it through some tests, as you'll be seeing later on molecular docking, it may not pass. So because it could have some steric hindrances. So that's why it's always good to have at least 3 options from, you could use Swiss model, another modeling tools or modeler like iTester. So I could just put those ones on the chat box. So from my end, Swiss model is completed. So are we on the same page? Mine is completed. So Swiss model gave us 4 models. Are we all here? Okay. So if we look at these models, Swiss model used 50 templates and then gave us predicted 4 different models. So to be able to go for the best one, we are going to use either the Z-score or the Q-mean. So if you click on, you pick the one that has the highest Z-score or the Q-mean, that has the highest similarity with your protein. So let's click on the model 4. And there's a way Swiss also does the ranking, which is also a good one. You'll see model 1. And if you look at the GMQE score is 0.98, which is, 0.94, sorry. The second model is 0.45. The other one is 0.51, the third model, while the fourth model is 0.45. So you can click on model 1. Also, before, click on this model 1. And the information we have is that it's used the templates from AlphaFold. So we can see, we'll see this code, which is actually the same thing with what we saw on AlphaFold. So this model, this is, you have similar, yes, this is exactly what you have on AlphaFold. So you can decide to download all 4 or go for the best one.
Teacher, please, sorry to interrupt you. Please, you were
Okay.
explaining something, but I didn't really get it. You said we should look for the one with the highest Z score or QME or
Or
something.
QMQE score.
Okay. From what I
Yes.
can see on my screen, my
Okay.
model 1 has a GMQE score of 0.94.
Exactly.
Model 0.51. Model 3 has 0.51. Model 2 0.45, and like that. So which one is actually the one I'm supposed to pick?
So you can go for the highest, but let's do something. We could do summary. Click on summary. So when you click on summary, it's going to give you all those models and the percentage sequence identity. Are you on this page?
Yes, I am.
Okay. So you're going to see the first one shows 100 and is a monomer.
Okay.
And then it gives us the information that is from AlphaFold.
Yes.
Okay. So why the second one, this 6ZE0.1 is a PDB code. And it shows that it's an homodimer and it's alcohol dehydrogenase. So which already cancels out this part, this one, because we are not interested in alcohol dehydrogenase. Is that good?
It is. Thank you. So, indirectly, you are saying that we are going to pick the first one that
The
has
first one,
100,
yes.
and
Yes,
it's a
the
monomer.
first one. Yes, which is a monomer. So if there are no alpha fold sequence, so for some protein, you may not have it on alpha fold, then you go for the Q mean. That's what will determine what your choice will be. So you pick the one that has the highest Q mean, which is this 0.64. And that's the model 2. Is that good? Okay, so it depends on whatsoever you have, but the Q mean can determine what you pick, or the GMQE. So if you click this, it's going to give you information of what that is. You see the Q mean is the same thing as the Z-score analysis. So you can, that was why I said you can either use the Q mean, which is the Z-score analysis, or the global model quality estimates, which is the GMQE. So once you click on that question mark, it gives you the necessary information for your choice. So I hope that helps. So I'm back. So since we've decided to go with the first model, we just click on this model 01 and then download it as a PDB format. Then I have it downloaded. So once you have the PDB format downloaded, then you can open it on PyMo for further analysis, and then whatsoever docking tool you want to use, it could be Autodoc, Vina, or Maestro, and then you can continue your work on the protein. So I hope that helped. So I think this way I'll stop if we don't have questions. I've already put in the link for the, okay, let me put that of iTesa in case we want to use iTesa. So the essence of all of this is for you to get a good structure to work with. But for the iTesa, you need to create an account. Okay, I'll go back to how we can download it. So that's for iTesa. So on how to download it, and back to this point, can you see module 1, structure assessment? So just click this, there's a drop down. Can you see that? Then you click on the PDB format. Then it's going to download like that. Then you can also click on the structure assessments. It's going to give you the Ramachandra plots, which is a good one. So it gives you several other informations. If you click on the structure assessments, if you want to download the Ramachandra plot also, you can. Then to give you the several scores and the likes. So I think that's all for homology module. It's an easy tool to play with, even with the other one, the Pyrex. Is just almost similar. Just paste your amino acid sequence in the the software, the database you want to use, and it's just going to run the job for you. And the same thing goes for ITESA also. So if you are using ITESA, just put in your sequence, and then it's going to bring out several models. So with the scores, the Z scores, you can predict which one will best fit for your protein of interest. So I think with that, I would like to stop it today.
Thank you very much, Dr. Anna.
Yes, ma'am.
Please, if you have any questions, you can speak up, or you can drop it at the chat box. Probably there's an aspect that is not clear to you, so you can speak up and ask any question.
Thank you so much, Ma, for the class. Please, I have a quick question.
Okay.
You said we shouldn't use just one structure, that we should have so many structures. Are you trying to say that we should get a structure from probably different softwares for the docking, or what exactly were you speaking about? Please, I didn't get that part. The reason why we need to not read, we do not need to rely on just one structure. Thank you.
Okay, thank you so much. That's a very important question. So what I meant by don't just use one structure is because once you get to, I think that should be the next lecture that Dr. Fatoki will be taking. Once you get to molecular docking, there are some tests you are going, or analysis you put your protein structure through. So if it doesn't pass, okay, I could use like steric hindrance, for example. If it has large steric hindrance, that may affect your further analysis or your molecular dynamics simulation. So you may not get like a good interaction between your target protein and your ligand. So by the time you want to do molecular docking and you put it through those several analyses that will help you to pick your best protein structure. And there are several things. I know that Dr. Fatoki will talk about it, but the one majorly I know is usually like a problem is steric hindrance or steric clashes. So if the atoms on the protein are clashing, then that may not be a good fit. That may not be a good structure for you to work with. So that's what I was saying, have several. So if you can run it through ITESA, through Swiss modeling, then if it's on AlphaFold also, it's good. And then if you run those several test analysis, that will help you to be able to pick your best structure for your further simulations that you may want to do on protein, on complex interactions. So I hope that answers the question.
Yes, ma'am. Thank you, ma'am.
Do you have any other questions? I think there's an hand raised up. If you have a question, you can ask. Otherwise, we could start the next lecture.
Thank you, Dr. Hannah.
Okay, ma'am.
In the absence of any further question. Yes, question. Come and ask it.
Thank you very much for the class, ma. I want to ask, why do we need to blast before copying the code? Because when we imputed our our protein of interest on UniProt, it brought a code like a protein sequence. Why can't we just copy that sequence and go ahead to?
Okay, that's a very good question. Thank you very much for the question. So the essence of blasting is is for us to be able to get templates, a template structure. So if you remember, like I showed before, in the Swiss model platform, you have opportunity to model your protein tertiary structure without a template. And there are also opportunities to use a template. So the first one we picked was the sequence because we did not have any templates. So what Swiss is going to do is that it's going to go ahead to look for its template by itself. So if you look at if you look at this, I think I stopped sharing. Let me share my screen again. Okay, so if you look at this, can you see this interface? You're going to see that Swiss used 50 templates to build this structure, these models. Swiss used about 50 templates. That's because we don't have our own templates. So I'll go back one step backward. You'll see on this interface where I have now that, so the essence of blasting is for us to see if we can get a protein that is close or similar to our own protein that has been crystallized already and is already in the protein data bank. So if we, through the blast, get a protein that is actually similar to our own that has been crystallized, then we'll just use these users templates, and that will give you the opportunity to upload your own templates. And Swiss is just going to use your templates to model your protein of interest. So I hope that helps with the question. So that's the reason for blasting, to be able to get the templates for our target protein.
Thank you very much, Dr. Anna. I think there's another question.
Yes, I'm trying to read. It says, if suppose our protein of interest has been crystallized on the PDB side, is it that we will just copy the code and paste on the Swiss website for modeling? Okay, thank you very much. That's a good question. So if your protein of interest has been crystallized, then you are good to go. You don't have to build any model again. Just use it directly. Use the PDB directly from the PDB. And that's a very good one, because if it's crystallized already, that makes your publication solidified because the protein has been worked on. So you don't have to do homology model. But if you have to do homology model, then you really need to convince, in order to be able to publish your work, you must be able to do a solid job to show that this protein you are working on is actually as it will be if it has been crystallized. So the whole essence of homology modeling is if your protein has not been crystallized and is not on the PDB. Okay, so there's a question on Ramachandra plots. So the Ramachandra plot is just telling you your amino acid that are in the allowed region, not allowed region, or the forbidden region. So if you have glycine and proline can be on the forbidden region, it will still be allowed, it will still pass. That structure will still pass. But if you have more than glycine or proline in the disallowed region, then your structure will not pass for docking. So you must be able to do those tests that I said that you have to do before to ensure you can do loop refinements. So there are a lot of things involved. I don't know if Dr. Fatoki will be able to get to those points in molecular docking. So you could do loop refinements to ensure that the amino acids that shouldn't be in the disallowed region are actually not there. If you have just glycine and proline in the disallowed region on the Ramachandra plot, then you are still good. You are good to go. But if you have any other amino acid in the disallowed region, then something is wrong with the structure. So you have to do loop refinements. And there are some other databases also to do loop refinements. You can use mode loop. And I know Maestro Scodinja has a loop refinement platform also. So there are several things to do to make your structure good for further analysis. So there's another question that says, after pasting your target sequences, what do I need to do on the Swiss model? You build the model, just do the same sort of things that we did for the one that we didn't put any targets. You just build the model. So once you build the model, it's going to bring out your own structure. So I hope that answers the questions. Stavuki, over to you. There are no more questions.
There's a question regarding pasting your target sequence.
Yes, that was what I answered. I said, once you paste your target sequence, just build the model. If you remember, like we did, okay, let me share my screen again. So can you see? So once you put in your, let me see if I still, okay, I don't have this again. Let's see. So I already put in my amino acid sequence of the protein I want to, the protein folding I want to predict. Then you see add templates file. If you have a model, okay, I could just quickly download 3DH from PDB. Just one second. Okay, so I downloaded the templates already. So just upload it from my computer. Okay. So if you see, I've uploaded the 3D etching. So what I'll just do is to build model. So once you build model, it's just going to work with that one alone. It's not going to go ahead to search for model for it by itself. So we'll just use this model. So does that answer the question?
There's another question.
Okay.
I think she said she lost connection when you were explaining Ramachandra plots.
Okay. So what I explained about Ramachandra plots, there is an allowed region, disallowed region, and forbidden region in Ramachandra plots. So Ramachandra plot is just to help you with how, will I use the word good, your structure, your protein structure is. Glycine and proline are allowed to be in the disallowed region. So if you have any other amino acid other than glycine and proline, then that shows that the structure isn't great. But if you just have glycine and proline in the disallowed region, then you can go ahead and use that structure. It's okay. But if you have, let's assume you have tryptophan in the disallowed region, then it shows that there's something wrong with your structure. So what you can do, I said you can do loop refinements, and the next speaker may probably take us through loop refinements before molecular docking. So you do loop refinements to treat, if I can use that layman's word, like to treat your protein structure to make it good, so that the tryptophan will not be in the disallowed region again. But if you have just glycine and proline in the disallowed region, you can go ahead and use your structure. So I hope that explains it.
Thank you very much. Is there any other